Now before I begin, let me just say I am using an op-amp chip. Everything else is just BJTs and resistors, but I'm using one op-amp chip. In the future, I do intend to do a video on making a homemade op-amp, but for now, just take a deep breath or two, because that's going to be its own thing. So the standard timer has 8 pins. We've got VCC and ground, fairly standard, and they'll be limited by whatever the parts I'm using can handle. The cont pin, which I still don't know why it's called that, probably control, but the internal timer works on 2/3 of supply and 1/3 of supply as its comparison voltages. Cont is where you specify the higher comparison voltage and the lower is half. It basically just overrides the internal voltage divider. Reset, which is active low. According to the internet, there are various different ways that this reset pin can work on different chips, but the natural one is reset resets the chip. It basically turns it off. Output high is on, output low is off. So reset low would be asynchronous turn chip off, basically. You've got out, which is going to be a push-pull, so it's low impedance. So it can actually drive a load, not a fan, but the 555 timer is designed to drive a reasonable load, where reasonable is, digital logic kind of current draws. Discharge is just the same as out, basically, except half of it. So out is high when the timer's on and low when the timer's off. Discharge is high impedance when the timer's on and low when the timer's off. So it's usually used to discharge the capacitor if you've got it hooked up that way. And then you've got threshold and trigger. When the threshold voltage goes above the high comparison voltage, the timer is supposed to turn off. When trigger goes below the low comparison voltage, the timer is supposed to turn on, so you can think of trigger as active low if you're using it digitally, unless reset is low, in which case it'll never turn on. Internally, this uses an SR latch, so it is invalid. Both threshold and triggering, so threshold high and trigger low at the same time, is invalid. You're going to get different results in different chips probably. I mean, it's not going to hurt the chip, but who knows what it's going to do. So there's your 8 pins. So we begin with the internal voltage divider, 3 resistors that are the same value, it doesn't matter what. Just decide on how much power you want it to dump and how much responsiveness. More resistance means less power wasted, but more resistance also means slower response to changing voltages, and also less noise immunity. One common value is 5,000 ohms, 5 kilo ohms, and it's a myth that that's where the 555 timer gets its name. They just called it 555 because they were creating a 500 series and the number was available, and the guy's like, 555, that sounds good. But you can choose 5K, I'm using, I don't know, like 15K, 22K something. Just make them equal. Connect your cont pin there, and that will override the voltage divider so that the high comparison will be cont and the low comparison will be half of cont instead of it being 2/3 and 1/3 of supply. You don't need any resistors on cont because it's going into a voltage divider, so you can just hook it right in. So I will call this the HREF signal and this is the LREF signal, and we've already got 3 of our pins taken care of. So now we have our 2 op-amps or comparators. I'm using the op-amps as comparators in open loop form, so you can use an actual comparator if you wanted. Power them with VCC and ground, of course. And I'm going to be using standard series configured NPN BJTs as NAND gates to make my SR latch, which means it expects the S signal, such as set, and the R signal, such as reset, are both active low to go into the NAND gate. So set signal is supposed to turn the output on. So when trigger voltage goes below the LREF, then we want it to be signaling to set, but we need to invert it. And if you're using op-amps as comparators, to invert the signal, you just flip the inputs. So instead of saying, is trigger less than LREF, we say, is LREF less than trigger? By doing that, whenever trigger is greater than LREF, this is going to be putting out a high. It's going to say, yes, trigger is greater, because we want low to be the active signal. When trigger is not greater than LREF, when trigger is less, it'll put out a low. Easy enough. So here we do the same thing. Usually when threshold is greater than HREF, we want to put out a high and say reset. but we want to put out a low instead to set a reset signal, so we flip it. When href is greater than threshold, when threshold is not greater, then it's putting out a high. Whenever href is not greater than threshold, it'll put out a low. So there we go. So that's the S and R signals that go into the latch. And that's the threshold and trigger pins taken care of. So here I have two NAND gates, a 2-input NAND gate and a 3-input NAND gate made with NPNs. This one is going to be the S gate, and this one is going to be the R gate of the SR latch with the feedback. So the S0 signal goes into here, and that's the Q output. That's the non-inverted output, so high when on. The R signal will go in here. I keep saying R instead of reset because we have a reset pin, so I'm just saying R. And that means this is Q0. So the feedback over here, this gets Q0, and this gets Q, and that is the SR latch, the standard no frills design. And then over here is our reset pin. So we just plug in that extra input, so the R signal coming in from the comparator or the reset signal coming in from the outside world will both try to reset the latch. And remember that an SR latch is invalid when both S and R are true. In other words, they're both low because they're active low. So if both comparators are signaling at the same time, if trigger is below the LREF and if threshold is above the HREF at the same time, then you get wrong behavior. Now you might say, we guarantee by saying don't do that S and R are not going to be set at the same time, but you could have S be low and reset be low at the same time. You could do that, and that's technically an invalid state, but if reset is low, then this NPN is off, which means Q0 is going to be high, and if S is low, then this NPN is going to be off and Q is going to be high. So two high outputs, so it's invalid. But we're not going to use both, we're only going to use Q0. I'm actually not going to connect Q to anything except the feedback. Q0 is our canonical output, and this turns out to be handy in a minute. But by doing so, we get the right answer at this moment, because when reset is low, the thing should be off. So the output should be low, and Q0 is inverted, so it's high. That's correct. Now, how do we get out of the invalid state? What if reset goes high? We turn off reset, but S is still low. In that case, we know that R is not low, R is high. We know that because we've said, don't do it wrong. So we know S and R won't be set at the same time. The problem is reset. So reset is high, R is high. And this feedback, we already knew that was high. So all three of these are high. So immediately Q0 goes low. We got the feedback here low and low. So Q is high, and we're good. We have re-entered a valid state, and we're getting the correct answer. The timer is on, so the output should be high, so the inverted output should be low. Now we go back and we say, S is low, reset is low, and instead of turning reset high, we turn S high. So reset stays low, S goes high, and then that's just a valid state for the SR latch. Because Q0 was high, which is the correct answer. So Q0 is high, and S went high. So these are both open, so Q goes low. Now we got Q0 high, Q low, valid state. So it's technically invalid if we're using the Q, but the Q0 always stays correct. So we just use Q0, and we're good. Now for the discharge output. It's an open collector NPN. Very, very easy. So the discharge pin is just the collector here. It's just straight up that. No resistance or anything. We want it to be controlled by the user how much resistance they use. And then we put into this the Q0 signal. We want the discharge to be open to ground when the timer is off. That's the idea. When the timer is on, if you're using a capacitor in, monostable or astable form, then the capacitor should be charging while the timer's on, and when it reaches a certain value, the timer flips and you discharge the timer, or the capacitor on the timer, through the discharge pin. So the output would go low and then discharge would open up. So when Q0 is high, that means Q, whatever it actually is, but the conceptual Q would be low, as in the timer would be off. And if Q0 is high, then the NPN is open. So we don't have to invert it or anything. By using Q0, it drives discharge directly. Excellent. So that's that. That's discharge. Now we can ignore it. The final thing to do is the output, which we want to be a push-pull. Now what you could do is you could just invert it, because you've got Q0. You could just hook up an NPN inverter, and you would get the correct answer. You would have a signal going out, but you would have uneven. Here, let me show you. So if you just do this with the Q0 signal, because we can't use Q, because Q would be invalid if S is low and reset is low, which could occur, but Q0 will always be correct. So we invert Q0, there's your output, you get the correct answer, but you have uneven impedance. So if the output is high, then it's going through this resistor, and if the output is low, it's not. And, you know, standard inverter, you don't want a small resistor here because you'll dump a ton of power whenever Q is on and you're getting a low output, because it's basically a pull-up resistor. It's just the transistor with a pull-up resistor on the output. So if you just want the signal, you can do that. If it's not a problem, that's easier. You don't need a push-pull. But the chip, the standard timer, is supposed to have a push-pull. Now, the fancy chip is going to have a fancier push-pull. It's going to, or totem or whatever the thing is, but I'm just going to do a very simple BJT push-pull that works great. And here it is. Your output is the collectors. Q0 goes to both of these. And it's super elegant once again because we're using Q0 and we were able to drive the discharge output directly with Q0, and we can drive this with Q0 as well because this is naturally inverting. Because a high signal is going to turn on the NPN, which connects to low, and a low signal is going to turn on the PNP, which connects to high, so it inverts. So it's perfect. We don't need any other shenanigans. We accidentally had the perfect setup, and there's your push-pull. But now, because we're using BJTs, there is one little unfortunate snag that cost me a few hours of my life before I simulated it and figured it out. And of course, if I had been formally trained, I'm sure I would have noticed immediately. Although if I'd been formally trained, I wouldn't be doing this because I'm doing this for fun. But the PNP transistor, the current goes out the base. Where's the base going? The base is going to Q0, which is connected over here to an NPN base. So we have positive through emitter base, through resistor, through base emitter to ground. The PNP in the push-pull output turns on the feedback over in the SR latch. Oops. Oops. So one solution is give up, but the other solution is buffer it. And fortunately, we can add parts and buffer it. It's unfortunate that it's necessary, but of course we're doing this just for fun. In the real world, you would just put a little 555 timer chip in your board and use that. But the easy solution is a double inverter. So we take the Q0 signal, we pass it through an NPN inverter, and we pass it through an NPN inverter, which is a buffer. It just inverts it twice. So now you can have current coming in from the PNP, and it's going to go down into the ground of this NPN instead of back there. So a double inverter is a buffer when you have a situation like this. Those are the only parts that I consider an unfortunate waste. If we'd been using MOSFETs, this wouldn't be the case. And this is also a reason why there are fancier outputs than this in a real 555 timer that's based on BJTs, but it works. There it is. So let me show you in action. Let me show you the overhead view and then I'll zoom in. So I'm going to be using this power supply with 6 volts. This is going to be the VCC and ground. I'm doing 6 volts because it divides easily by 3, so it's 2, 4, 6, just so it's easy to look at. This second power supply is going to be giving out my cont signal, so I can show that that works too. And then I'm going to be using the oscilloscope just to provide a third variable voltage source. I didn't want to use a voltage divider because I've got it going into whenever I use a voltage divider as a voltage source and I'm using resistors, I end up with the voltage divider as a voltage divider inside the whole thing, and it just so either I have to buffer the voltage divider or I can just plug this in. So I just plug this in. If you had a third power supply, use that. And then this multimeter is going to show the voltage on the oscilloscope because it's easier to read. Over here, I've got a little breadboard and a big one. The big one is the actual chip, so this would be the 555 timer, and over here is the stuff hooked up to it, so that it's clear and separated. So I've got the first power supply coming in here, I've got the oscilloscope signal coming in here and the multimeter plugged in there, and then I've got the cont signal coming in here. Over here, what I've done is I have 8 pins that simulate the 8 pins of the chip. From top to bottom, they are VCC, ground, reset, cont, trigger, threshold, discharge, and out. So this simulates hooking up the pins. So the VCC and ground are hooked over from the power. I have a switch here that will either completely disconnect it or give the cont signal. So this is connected to the cont pin, so I can either not have cont connected or it can be connected. Here I've got my reset signal, so just a SPDT switch, high and low to the reset pin, and I've got 3 pairs of resistor and LED for output. The yellow one is connected to discharge, so when discharge is low, this LED will come on. When discharge is high, the LED will turn off. And then I've got a red connected to output and a blue connected to output. The red indicates high and the blue indicates low. So one of those will be on all the time because it's a latch. So even when the voltage is in the middle, the latch will be giving a solid output. Then over here is the actual chip. So VCC and ground come in the corner, and I've got the voltage divider, 3 resistors forming the voltage divider here, and cont is connected to the first one. The 2 of them give the high and low ref, which I have brought over here for organization. This is how I can make boards that look this ridiculous and they work fine because I do it piece by piece and I'm organized. So here's href and lref from the cont pin and the voltage divider. Here's my op amp. It's 2 op amps in 1 chip, and I've got the trigger and threshold pins and the H and R ref, and then the outputs are the S signal and the R signal, which are over here. The S signal and the R signal come over here. So I've got the 2 input S gate and the 3 input R gate. So the inverter is here, the inverting resistor. And then the S signal comes in here and the Q0 signal comes in here. Here's the inverting resistor. The R signal comes in here. The reset signal comes in here, which is bridged over from the board. And the Q feedback comes in here. So this puts out Q, and this puts out Q0, which I have brought over here. So here's Q and Q0 that are connected back over here with feedback. Then I take the Q0 signal over here to the discharge open collector. So that goes out to discharge. Then I have the double inversion right here. So 1 inverter, 2 inverter, make a buffer. And then that is finally brought over here to the PNP and the NPN push-pull, which is connected to output. And there's the chip. You could make this much more compactly if you wanted. If I, decided to solder this, it would be reasonably small. It would be bigger than a 555 chip, obviously, but I've got a lot of extra wires and space for organization that you don't strictly need. Cool. So let me show you the chip in action. So right now, I've got 6 volts on this supply, which again is so that I can do 2, 4, 6 volts, easy in my head. And then here I'm going to use 3 for the cont, but right now it's disconnected. Right now cont is not doing anything, and reset is high, so it's not resetting. I've got the voltage on 0 volts, discharge is closed because the yellow LED is not on, and the output is high because the red is on instead of blue. If you can't see red and blue, it's the first one's red, second one's blue, third one's yellow. So right now the chip is indicating high, which makes sense because reset is high and the voltage is 0, which is definitely below 2 volts. So if I turn the voltage up, you can begin to see my signal voltage rise, 1.1 volts and so forth. So as I go over 2 volts, you can see nothing's happening, as it shouldn't. But when I get closer to 4 volts, right as I close the threshold to about 4 volts, the output turns low and discharge turns on. Because when the voltage on trigger and threshold goes high, then the timer should turn off. And now, if I turn it over 4 volts, it's fine. And if I turn it below 4 volts, it stays off. The timer is off until I reach about 2 volts, and all of a sudden, it turns back on. So when the voltage goes low, then, however you've hooked it up, the timing sequence is ready, and the timer is on. And that's the normal operation. Now, if I turn reset, you can see immediately, even though I didn't change the voltage, it turned off. So now reset is low. So I can turn the voltage up to 4, I can turn the voltage down, I can turn it up and down, and it stays how it was. Now, let's confirm that everything works fine. So when I put the voltage where the timer should be turning on and I disable reset, as soon as I do, it turns on just like it should. So let me reset again. If I turn the voltage up into the R region where it should be off and I turn off reset, then we're good. And if I'm in the middle, if I'm where both S and R are high and the latch is basically latching, it's not setting or resetting, and I disable reset, then the chip stays reset because there's no active signal to set it. The last known state was reset. So even though the SR latch inside is driven invalid when S is on and reset is on, it still works fine because we're using the Q0 output. Finally, let me show you cont. So let me turn reset. Okay, it already is. But if I turn cont on, now it should be, instead of 2 volts and 4 volts, it should be 1.5 volts and 3 volts. So if I turn it down, 1.9, 1.8, it is not turned on. As soon as I go to about 1.5, it turns on, and then it should not turn off until 4 volts, but once I get to 3, right about at 3, it turns off. So that's the cont pin, overriding the internal voltage divider. And there you go. This was one of those circuits that was incredibly fun, but also super frustrating, but only because, again, I didn't have formal training, so sometimes I forget the little tricks of PNPs, and in my brain I segment too much. Like, I had an SR latch, and then I had to push-pull, and it didn't occur to me that there would be interaction that way until I put it in a simulator as a last-ditch effort to be like, what is going wrong? Is something broken somewhere? And yes, as soon as I did, I saw the little current flowing through into the SR latch, and I said, oh. So other than that, it was really fun. I absolutely encourage you to do this. I mean, you don't have to. I ain't your mother. But I think that this was super interesting and an excellent learning experience. It reinforces, of course, the behavior of PNPs. But it's building a circuit like little Lego. It's fun. And it works just like a 555 timer. I have followed the spec. Although I'm not going to lie, it's a little easier to just use this. So I hope you found that as interesting as I did. I will definitely be doing a future video on homemaking an op amp and other things, but for now, I will be seeing you.